The next topic is filtering, and I think this is more interesting than noise. So before talking about the actual filtering operation, let's try to understand some of the basic concepts of which will be required. So if you go by definition, image filtering is what you do is you take a function which is called a kernel, and you take like a small patch from your image, and you just compute like you can say like a linear combination of the function with the image patch, and that will give you some value. So it's kind of an operation which is performed using that kernel function on a neighborhood of an image. Okay, and this is like a very general formulation for image filtering. In this case, I represents an image. Okay, so M and N are like any particular like your grid locations in your image space. And what you do is you look into the neighborhood of that location, which is centered at M and N, and the radius of that neighborhood that's defined by these two parameters, K and L. So how big that neighborhood will be. All right. And what you do is you have this filter function. You compute like a combination, or you can say linear combination of this function with the pixels in this neighborhood, and you do some kind of averaging, and that gives you like some kind of response. So this general formulation is called image filtering, where I is your image, F is your filter, and H is output, which is called like the filtered image. Okay, so M cross N are like the 2D coordinates in your image space. And again, K and L are like a 2D coordinates which define like how big your neighborhood will be. Now, the question is, I think this is a very basic question, like why we need filtering. And later you will see like a lot of different applications of filtering, even in like when you try to study convolutional neural networks and deep learning, you will see like the basic operation which is being performed as filtering. So that's one thing. But other than that, like that's more recent. In earlier days, people used to use image filtering for enhancing images. It could be if you have noise in your image, which you just look in the previous set of slides, right? There will be noise in your image. So how to remove that noise? If you have to perform resizing of your images, then again filtering is used. And if you have to perform like different kind of operations, for example, if you want to increase or decrease contrast or any other image manipulation, filtering is very useful. Okay, so that's one use which is called image enhancement. Then the second is like if you want to extract some meaningful information from images, then filtering is very important. And this correlates to like when I was talking about how filtering is used in deep learning. So we use filtering to extract the useful information which is used for making predictions. Okay? So this information could be either like texture present in the image, it could be edges, it could be like distinctive points, and many other interesting features. And again, you can use like to detect some patterns, and this also correlates to extracting useful information. You will see like how these two are very related to each other. And for detecting patterns, template matching is like one interesting use. And I think in the first lecture, we were talking about how we can use template matching for object detection. So we're trying to detect patterns, right? And there, if you remember correctly, we were using correlation. So that correlation is actually a filtering operation. All right, so let's see like a concrete example of filtering. Now on the left here, I'm showing you a very small patch of an image. So your image will be pretty huge, like it will have a lot of pixels, but let's just focus on a very small neighborhood of that image. And in this case, it's just 3 cross 3. And these are pixel values. Let's assume that it is a grayscale image, and these are the pixel values. Right? So, and in this case, you can see like the neighborhood is like neighborhood is 3 cross 3, and we are interested in this location. This is like the X and Y where we are centered at, and FP, let's say, is your kernel, okay, which is operating at this point P. Now, what will happen is when you apply this filter on this neighborhood, what this function will do is it will utilize all these values in some way or other. Right now, we don't know how it's going to utilize, but it will make use of all these values. And after doing that, it will come up with a number. Okay. And that number will replace the location which we are interested in. So this step is called filtering. So how these numbers will be utilized? There are many different ways that differentiates like different filtering operations, but that's like the high level how filtering is performed. Okay. So let's try to understand from a concrete example of a kernel. In this case, this is an image patch. Again, this is 3x3. And in this case, the function f I was showing you earlier, in this case, it's a 3x3 kernel. And these are the values. All right. So don't worry about like how we estimate these values or what this kernel is. Right now, just try to understand like how this filtering operation is being done. Okay. So just try to understand like the computation part of that. So what we do is we take this image patch, we take this kernel, and we just compute a linear combination of the values in this image with the values present in this kernel. And a simple way to do that is you can just perform element-wise multiplication of all these values and then sum up all those values. So if you remember this like from the linear algebra basics, this was called like head-emet product, right? So this is like you perform head-emet product and then you will just take average of those values. So it's a one step like ahead of that. And you will just replace the value of this pixel with whatever value you have obtained. Okay, so in a way, I mean, this is also a linear combination because what you're doing is you are taking a linear combination of all these pixel values. And to take that linear combination, you are using the values in this kernel as weights. So if the value at a kernel is 1, which means that you will give like importance of 1 to this pixel value because you're multiplying this with 1, right? So if you look at this value, you are saying it's 0. It means you don't want to pay any attention because this is going to multiply with this and it will become 0. So you're ignoring this pixel value. Similarly, you are ignoring this pixel value. So if you try to visualize this kernel, what's happening is all the pixel values on the left over here, they are being given like equal importance, right? This will result in like 1, 2, and 4. And at the center, not that much. You're just paying attention to like the center pixel maybe, but very small amount. And again, you are paying attention to the values on the right, but like the negative side, because all of these are negative values, right? And this will make all these values negative. Okay, we'll discuss more like the interpretation of the kernels. But basically, you just do element-wise multiplication, take average, and replace the pixel value. So this is like one filtering operation. Now, there are different formulations like which you can use to represent this filtering. And the basic one is called correlation. And the mathematical formulation for correlation is you have two different functions, f and h. And what you do is you perform like element-wise multiplication of these two functions over some neighborhood, like in this case, like k and l, if it's like two-dimensional function. And correlation is used to find out if two different functions are similar or not. And this you have seen in the first lecture when we're trying to perform object detection using pattern matching. If the patterns match, then we get like a very high response, which means the correlation is very high. So this is directly coming from statistics. Okay. In this case, what we do is if we have to use correlation to perform filtering, we represent the first function as image and the second function as kernel. So first function becomes something like this. The second function becomes this. So there's the image patch. This is your kernel. And the operation, if you go through like steps of this equation here, it's nothing but the steps I explained to you in the previous slide. You just perform element-wise multiplication and add those values up. All right. So that's correlation. The second way to represent filtering is convolution. And you might have heard of convolutional neural networks. We're going to study that in this course in very detail. Now, convolution, the mathematical formulation is almost same as correlation. We have two different functions, right? And again, we look into some neighborhood like of these functions. The only difference is we flip the second function. All right. So because we have these negative values. In correlation, this was all positive. And again, it's the same representation, F is image, H is kernel. Now, if you have to represent convolution in form of correlation, what you can do is you take your kernel, because you have negative values, you can actually flip it in both the axes, X and Y. So in this case, we are flipping like along x-axis. So this becomes positive. Then we can flip along y-axis, then that will become positive, right? Then it's exactly same as correlation. So let's say this was the initial kernel, you flip along x, flip along y, you get this kernel. And then again, you can just perform correlation of this kernel with the image patch. It's the same equation. Okay. So you can see like correlation, convolution, exactly same thing. The only difference is the kernel values. Now convolution, like it's associative. These are some interesting properties. We can quickly go over these. So associative means like if you are performing convolution of G and I first, and then convolving that with F, it doesn't matter like what order you use. You can actually first convolve F and G, and then convolve the result with the second function. Okay, so it's associative. Now, just going over the definition. So convolution, it's like a filtering operation. So is like correlation. And so convolution is kind of giving you how much is the overlap between two different functions. All right. And we have the negative sign, which means that we actually shift the we shift the kernel over our function, and we try to find out like if there is some overlap or not. But the high level intuition remains the same, because correlation is also comparing two functions and finding out whether they are similar or not. Okay, so the basic idea remains the same. Now, before going to like the actual some of like, we'll go through some of the examples to perform filtering. There are like two other concepts which are very important. We'll see. So first is mean, and you all must know this already. Mean will be like you have different values, and you add those values and divide by the number of values, right? So it's the standard mean. And again, I could be just a number, it could be a matrix, it could be a vector, anything. Right? Now, an advanced form of mean is weighted mean, which I think is more relevant to us. And this weighted mean is also related to, we have been talking a lot about linear combination. Okay, so if you look at the numerator of this equation over here, this is a form of linear combination of all these values, right? And these W1, W2, all these are weights. The only difference is you normalize this value. Okay, so basically when we will perform filtering, we will see that most of the time it's going to be linear combination like this, and we are going to normalize with like the number of pixels we are actually operating on, the size of the neighborhood. So this is actually showing the filtering operation which we are going to use. Any questions?
I have a question. In the function, we're talking about G, right? When doing the convolution operation, what does the associated property, what does the G represent?
G, it could be any function. It could be any function. In this case, we're interested in images, so we can say G could be an image. But in general, it could be any function.
Or can be a function, or can be a kernel?
Yeah, it could be a kernel as well, because it's kind of commutative as well, right? It doesn't matter whether you represent G as image or G as kernel. Yep. I could be image, or this could, the result will not change.
I have a question. So in the like the flipping part, where you like differentiated the convolution and this one. So here, like you said, minus k and minus l, multiplying it with minus k, like minus, is it like a horizontal and vertical flip? So I couldn't really understand like how multiplying a value with just a minus value is also flipping it. I mean, we are not flipping it, we're just not multiplying it with minus. So like for example, h1 should be minus h1, right? So the value here, whatever the value is,
right? So, yeah, h7 will be your negative of h1. So these k and l, these are not actual values.
These are indexes. These are indexes.
Yeah, these
right?
are indices. Right?
Oh,
yeah.
I see. I get it. Yeah.
So think about like if you have a coordinate system, right? You are going from negative x to plus x. So you just flip the x's.
Yes. Okay, that's good. Thank you.
What do you mean convolute another convolutional kernel like the f times g times the I? I understand the using the kernel to apply to the image, which is just like which is just applying every grid applied to them and then just sum them together. But what about the f times g when f convolute g when f and g are both convolutional kernel? Isn't that you just end up with one grid?
Okay, so in this case, let's say I is your image. Okay. And let's say, and again, this is just one example. I mean, we can have like a lot of other variations here. Let's say I is your image patch, G is your kernel, first kernel, and F is your second kernel. So we want to perform filtering on the image, let's say twice.
Yes.
So then you will perform filtering on I using G. You will get some result, and whatever result you have, you're again going to perform filtering using F. Right?
Yeah,
So
I
that could be one
understand.
interpretation.
Yeah, I understand applying the G first, then applying the F. But what about the right hand side? Apply the F to the
Right.
G.
Yes. Okay.
Where I
So,
confused.
all right. So whatever result you get using this operation, even if you just perform convolution of the kernels first, that will give you just one kernel. And if you use that kernel to perform filtering on image, the result is not going to change.
Yeah, I understand that it won't change, but I just couldn't figure it out how to convolute two kernels because for example, if we have a 3x3, right, then we just only update the center one, which is a 2 pixel, right? If it's a 3x3 image, then
Right.
how are we going to do that if we have two kernel? Is that the same? Then we just end up with a new FG kernel that only changed the 2 position. Then we use that new FG kernel applied to the.
That's a very good question. So we'll have an example later on. We'll talk about that. Okay, just wait.
Okay.
Okay.
Professor,
Yes, go ahead.
in the filtering slide, I couldn't understand how the filter output was filed. Like, can you show show how the calculation is done?
This
Yeah,
one.
this one.
So these are all one, right? So this is
Yeah.
going to give you 6, 7, right? If you sum up all these values, 4, 5, 6, and 7.
Yeah.
And
So
10 times 0.1 is going to give you 1. So that becomes 8.
so we are
And
multiplying all.
okay, so let me go over again. So this one has a weight of 1. That will give you a 1.
Yes.
2 will give you 2. 4 will give you 4.
Yeah.
This becomes
Yeah.
7. That's
Yeah.
true.
Yeah.
These two become 0.
Yes.
10 will become 1.
Yeah.
So you can add 1 to like 7. That gives you
Oh.
8.
Oh, so
Okay.
this is not a multiplication. It's a convolution sign. So it's just one number. I was thinking if it was a matrix multiplication. Okay, got it. Sorry.
Okay. All right, good. I think there is another question. How can we define kernel values? That's a very good question. And that's, I think, a major portion of this course, how to learn these kernels. We'll talk about that when we start going through convolutional neural network. And I'll also show you some other interesting examples of these kernels. Okay, but that's a good question. So we'll talk about like how to come up with values for these kernels. Any other question before we move forward? All right, good. So the next topic is we studied like how to perform filtering. Now we're going to go over some of filtering examples and really see like what filtering means in images. Now before doing that, let's try to understand some basic filters. Now the first one is Gaussian filter, and Gaussian filter, this curve you have seen before. This is a Gaussian curve. All right, it's symmetric across the mean value, and towards the left it becomes 0, towards the right it becomes 0. So it gradually decreases as you move away from the mean. And this is the equation for this Gaussian kernel. So this is one-dimensional. What you can do is you can also have like a two-dimensional Gaussian function. If you try to visualize that, it will look something like this. Okay, so it peaks at the mean. In this case, the mean is like two-dimensional 0 cross 0, the origin of the plane. And again, same to like this 1D Gaussian kernel, it's also decreasing. If you look
Professor,
like at this, yeah, we'll take questions later on.
okay.
So if you look at this Gaussian kernel from the top, we can actually represent that as a heat map, and the heat map will look something like this. Okay, so what this means is the black value represents completely 0, and the white represents a very highly active value. Right? So you can see that at the center, which was pretty high, we have like it's a high value here, right? So that's the center of this Gaussian. And as we move like towards the outer boundary, the value is actually reducing. And you will see like why this representation is useful. We can create like a two-dimensional kernel using this kind of visualization, where the center value in the Gaussian kernel will be very high, and the values which are far away from the center will be very low. All right. So this two-dimensional Gaussian, again, it's the same equation. Again, you will have just two axes for this. Now, looking at the one-dimensional Gaussian filter, so what we do is we take this Gaussian curve and we discretize the values to create the kernel. And here you can see that this is the center of the Gaussian, and it's 1, which is kind of like the maximum value we can have. And you can see that as we are going towards the left, the value decreases. So we are at 0.6, 0.13. It's almost going to 0. And if you move towards the left, it will be almost 0. And again, if we go towards the right, we can see like it's kind of symmetrical. That's a property of Gaussian. So the values won't change, but again, they will reduce and again, gradually becomes 0. So this is like a discrete Gaussian 1D kernel. Now, similarly, we can form like a two-dimensional kernel for Gaussian. Instead of a vector, it will be a matrix. And again, we'll have a very high value at the center, and the values will gradually reduce as we move away from the center. Now, why Gaussian is this important? So you will see like Gaussian is coming up again and again. I mean, you have like your statistics course, right? In your probability course, you might have seen this a lot. So one simple example, like the plot I'm showing here, even in the class, like if we take like all the female students, right? And if we will try to measure like the shoe size for them, you will see that if you try to plot a histogram for that, it's going to be a Gaussian. Okay, this is just one example, but if you take like enough number of samples, it will look exactly like a Gaussian. And this is not just true for like female shoe size. Even like in the class, if we just measure like the height of all the students, it is going to be a Gaussian. And most of the times, like the grades we receive, it's very close to Gaussian. Very hard to get at a Gaussian curve, but most of the time it's kind of a Gaussian curve there as well. Okay, so it's like it's a distribution which is it's very natural, and you will see like in your 3D environment all the time. Okay, it's like the most common natural model. And there are a lot of interesting properties of Gaussian function. So first of all, it's a very smooth function. It's symmetric. And again, we'll talk about derivatives later on, why derivatives are important. So one interesting property of Gaussian curves is like you can keep computing derivative of that function, which I was showing you earlier. It's going to be Gaussian every time. Okay. So, and again, if you compute Fourier transform of Gaussian, it's going to be Gaussian. We'll briefly cover this aspect in, I think, one of the lectures. And if you compute convolution of a Gaussian function, like convolution of two different Gaussian functions, again, you will get a Gaussian function. And this is really important property. We have a lecture on this where we'll use like to extract some meaningful features using Gaussian filtering. And this property is like if you have a 2D kernel, which is let's say if it's a Gaussian, then we can perform that 2D convolution operation as two independent 1D convolution operations. And the reason we do that is like 1D convolution operation is very efficient. We'll talk about that as well, so don't worry about it right now. But it's a very interesting property of Gaussian. And this is again just a fact, like we have cells in our eye that actually are performing Gaussian filtering. So earlier we were talking about how noise is introduced in images, right? So then I was saying, what's the true color? And there were a couple of questions. Again, even if we know the true color of, let's say, an object, a chair, right? But again, what we are observing, there can be like a lot of noise in between how we are observing it. Again, it could be like the lighting condition, the light might be very dim, there might be some dust in air, right? So there is natural noise present there, and we have this Gaussian filtering going on when we form this image in a retina. So that filtering operation is being performed to denoise that image. All right, so let's talk about some interesting filtering examples. Now, this is your input image. You have seen this image a lot. So we are going to use this separately in this course. This is a very famous like Lena image. And in this case, this is our kernel. Okay, so you can see the kernel is like all zeros and it's one at the center. Now, I mean, most of you can easily guess, like if we have such a kernel and we perform filtering using this kernel on the input image, it won't change anything. The image will still remain the same. So if you try to visualize this kernel in two-dimensional, it will look something like this. The center is pretty high and all the other values are 0. And the reason it's not doing anything, because if you try to use the neighborhood values, it's saying everything is 0. So it's kind of enforcing that you don't use anything from the neighborhood values. Just use whatever you have at this particular location. And if you do that, it's kind of you are not changing the image. So it won't change anything. All right. So again, but this is a filtering operation and this is a kernel. Now let's see some variation. Let's move that one towards the left. All right, it will look something like this. So don't worry about the orientation of this plot. It's just saying that, okay, now the weightage is being given to like a pixel, which is like neighboring of this, the pixel which we are interested in. Now, I mean, you can perform the filtering operation, which we discussed the equation, but if you try to think intuitively what's happening here, what we are doing is we are actually not using any of these values, right, in the neighborhood. And we are even not using the value itself in which we are interested in. But what we are doing is we are using the value which is on the left. So if we, Teja, can you please mute your mic? So if we use this value, then essentially we are actually taking this value and storing at this location. All right. So now what will happen is your image will shift. And you can see that since you are moving values from left to right, your image is going to move from left to right. It's just a shifting operation. So now you know that, I mean, using this kind of kernel, you can actually perform shifting in your images, which is very interesting because this is a very simple kernel, right? Similarly, you can actually have one at any other location and you can perform shifting. For example, if you have one over here, it means that you are shifting the image diagonally. Okay. Now, this is another interesting kernel. And in this case, what's happening is we are actually paying equal attention to all the pixels in this neighborhood. Right? And you can see here that we have this normalization factor, and that's due to like we don't want to mess up with the pixel values, right? So we want it to be normalized. And the normalization is coming from summing up all the values in this filter. Earlier, we didn't need this because we just have one. So if we divide by 1, it won't change, right? Usually we normalize our filter. So we have 9 different values and the kernel is actually normalized. In this case, what's going to happen is you're saying that if you're focusing on this pixel, please also look at all the other pixels in the neighborhood. All right, so let's see what's happening. It's kind of smoothing your image. So this is in a way like you can say a blur filter or a smooth filter. So it will smoothen your image. Okay, later we'll see like how this is useful. This is another example of the same blur filter. In this case, a filter is slightly bigger. This was a 3x3 filter. In this case, it's a 5x5 filter. All right, and again, you can see that normalizing factor, it's 25 because all of these values will sum up to 25. And again, you can estimate that what's going to happen. This is going to smooth your image. But if you compare this smoothing with the previous one, this is like much higher smoothing because you are considering like a bigger neighborhood, right? In this case, it's 5x5. Earlier it was 3x3. You can keep improving the increasing the size of the neighborhood, and then your smoothing will keep increasing. Okay, so that was like a very simple smoothing filter. Let's talk about Gaussian smoothing. So this is a Gaussian filter, and you can see that the center of the kernel, it's pretty high. And as you move towards the neighborhood, the values are going down. So this resembles like a Gaussian kernel, but it's kind of a discrete form of Gaussian function. Okay? Now, again, if you perform like filtering using this kernel, you can see again, it's kind of smooth, but it's not very distorted. You can say like it's not that bad when you're filtering using like all ones. So this is slightly better than the previous filter. And that's one of the reasons why Gaussian filter is used in filtering. And the reason for this is you can see that whichever pixel we are focusing to, we are actually giving more weightage to that pixel. And as we move away into the neighborhood, the weights are going down. So it kind of say that, okay, you're not completely ignoring the neighborhood. You are still using those values, but not that much. Okay. Now let's try to compare the smoothing operation using Gaussian and using averaging. So this averaging is like the filter which I showed you earlier, where you had like all ones. You are giving equal weightage to all the pixel values. So this is Gaussian smoothing, and this is smoothing by average. You can see like this is much more better than this image on the right. Now let's try to understand what will happen if we have noise in our image. Okay, so the original image which I showed you earlier, we try to add like some additive Gaussian noise, and don't confuse this Gaussian noise with Gaussian filter. Gaussian noise is something which we discussed like earlier in the lecture, right? Again, it's coming from Gaussian distribution, but we are adding those values which are coming from the distribution as a noise. Okay, so we have this image which is noisy. If we perform average filtering, we'll get something like this. And if you perform Gaussian smoothing, we get something like this. So I mean, it's hard to say which one is better. But again, in this one, we are kind of losing the texture, right? We are smoothing the image a lot. But in this case, we are getting rid of noise, but it's not that great. But still, we are not losing the fine-grained information which is present in the image. Okay. Now, another interesting filter is box filter. This we have seen earlier as well. So what it will do is, as we discussed, it will just replace like each pixel location with average of its neighborhood, right? So let's try to understand that on this example, because earlier we couldn't understand what really is happening. So this is a more concrete example here. Let's say this is an image patch, and so all the dark pixels, these are all 0. And we have like some bright pixels which have value of 90. All right, so let's say this is your image patch, and let's perform filtering using this box operator or box filter. So what will happen, you will first place this filter at this location, right? And you perform filtering. What's going to happen, you will get all 0 because all these pixels are 0, right? Then this will be the next location. You move like towards the right. And here you can see like all of these are 0. This is 90. So if you take like average, it's going to give you 10, right? Because all the other locations in the filter will become 0. Only this will give you 90. And if you divide that with 9, that's going to give you 10. And you can keep doing that for all the locations. I'm not going to go through all of that. Let's talk about like at this location. Okay, so these 3 on the bottom row, these are all 0. And this is also 0. So if we just try to like a quick math here, we have 4 pixels which are 0, and we have 5 pixels which are 90, which means this is going to give you like maybe 10, right? Because Okay, hold on. So you have 3, 4, 5. That will be 450. If you divide that with 9, yeah, 50, right? So, okay, so you just add these values. This will be 450. Divide by 9. That's going to give you 50. Okay, so this is you can see like a missing pixel. Then you replace that with the average value. At this location, what's going to happen? I mean, the values won't change, right? Because all the neighborhood, it's the same set of values. Everything is 90. So it will still be 90. So now you can see that how the smoothing operation is being performed here. You will see like at the center of this region, the values are actually not changing a lot. Most of these are still 90 because the neighborhood was 90. So again, same is the case with like where you had all zeros. But the effect is like when you have a boundary, when you're moving from 0 to 90, right? You have an edge. There you will see that your filter is actually performing this smoothing operation because these values are changing. Okay. And this is deliberately put there. So this is a 90 and you can see this could be an outlier. Now, if you perform smoothing, you can see like this reduced to 10, right? So in a way, if you use box filter, you're actually getting rid of these outliers. So this outlier is not present in this filtered image. All right. So this could be like noise or something, which is removed by this filtering operation. All right. So what it's doing is it's smoothing and it's trying to remove sharp features. For example, if you have edges, it will smoothen the edges. So this is like a very extreme case of box filtering. You can see that like all these sharp features, they are completely gone after box filtering. All right, so this is, you might remember like this eye of a very famous like scientist. And now you know that you have this filter, if one at the center, not going to change. If you have one on the right, you know that the image is going to shift towards the left. Now there was a question like the use of multiple kernels, but still we are not there yet because this is not like a filtering operation. So this is your first kernel, which is kind of saying that okay, give more weightage to the center pixel. All right, and this is like a smoothing operator or a box filter. Again, trying to normalize this, and you can see that it's 2 because if you try to normalize like all the values or the resultant values, the sum will be 1. Okay, so it's still like a normalized kernel. So this is a very famous kernel, and this performs like sharpening operation. This is called sharpening filter. Okay, so you can see that this image, it was kind of blurry. So this filter is actually bringing back the edges. Okay, and the reason is because it's paying more attention to the center filter itself. All right. So that was the original image. And if you perform filtering using that filter, sharpening filter on the whole image, we'll get something like this. You can see that like all the edges like in the code here, they are recovered. So this is much better image than the left. All right, some more examples of filtering, and this is, we are moving more towards like extracting important features in images. So far we have seen like how we can perform smoothing operation or maybe remove noise. So this is a very special filter. This is called Sobel filter. It's used for detecting edges in your image. And if you use this for filtering, you can see you will get a result something like this. And what this is showing is, this is kind of showing all the vertical edges present in your input image. Wherever you have a vertical edge, you will get a very high intensity at that pixel location. Similarly, you can, so this is like the edge detection in the vertical direction. You can just rotate this. And again, this is part of a Sobel filter. In this case, we are trying to detect horizontal edges. Okay, so don't worry about like if you don't understand how we are getting horizontal and vertical edges, because we are going to cover that when we talk about derivatives and all that. Okay. So if you perform filtering using this filter on this image, you can see like all these are the horizontal edges present in the input image. Okay, so some key properties of linear filters. If we add the filters, that's similar to like if you perform filtering on the first and then add later. Okay. And again, it's kind of shift invariant, which means that it doesn't matter like where your pixel is located. The output is not going to change. Okay. So you can shift your image first, perform filtering, shift back again. So shifting is not going to change your output. And this is important because if you have an operator which is linear and shift invariant, you can represent that as a convolution operation. Okay, commutative, I think this property we have, oh, we didn't cover this again. So yeah, it came up. The issue is like, we were talking about one is kernel, one is image, right? And I said, it doesn't matter. You can have like this as image or this as image. The result is not going to change. So that's the commutative property. Okay. So you don't differentiate between your filter and your signal. Signal in this case is your image. Associative, we have seen this before. So that's good. And again, so this is also interesting. We saw one example for this, and this goes for the subtraction as well. So if you consider this as a filter, so you are adding two different filters and then perform filtering, the result is not going to change if you perform like filtering independently and add the result. Okay. The other interesting operation is about scalars. So if you are like scaling your image, it doesn't matter whether you scale first or you, let's say, you can even scale your kernel. That's not going to change it. All right. In this case, let's say you are scaling your image. In this one, you are scaling your kernel. And in this case, you are performing filtering first and then scaling the result. So all are similar. So this is identity operation, unit impulse. I think we saw one example of this when we just have one at the center. So this is one-dimensional kernel. But you can have two-dimensional kernel where you just focus on the center one. So your result is not going to change in that as well. All right. So I think this one should be the last one we cover today. And this is called median filter. So median operation, I think you should all know from your basic maths. All right. So what median filter will do is, in that neighborhood, instead of computing average or any linear combination, it will just select like the median value. All right. So we'll see like what are the advantages, and it's not same as convolution because we are not actually using the neighborhood values. So let's look at this simple example. I think it will be more clear. So in this case, when you are using mean filter is like you have a one like at all the places, right? It's normalized, and we know it gave you 50. Okay, what if we use like a median filter? Now, median filter will actually take all these pixel values in the neighborhood. So we just have 0 and 90, and it will pick the median value. And in this case, you can easily see that you have 4 pixels which are black, 4 pixels which are white, 5 pixels which are white. So definitely the white pixel is the median. All right, so the value will be 90 if you perform median filtering. Now, let's look at the example and try to understand like why median filter is better. So on the y-axis over here, this is just showing you the shape of the kernel. Right? So this is 3 cross 3, 5 cross 5, 7 cross 7. You are gradually increasing like the neighborhood of your kernel. And on the x-axis here, we have like different kernels. We have mean filtering, Gaussian filtering, and median filtering. So generally, you can see that as you increase the neighborhood of the kernel, your Gaussian filtering is actually doing a better job as compared to mean filtering. But if you look at the median filtering, even with like 3 cross 3 kernel, it almost removes like all the salt and pepper noise we had in this input image. Okay, so if you think about this, why that's the case, in median, we actually don't care about all the values which are present in the neighborhood. We don't perform any averaging. We just pick the median. So in that sense, we are not changing the pixel intensities. So it's not performing any smoothing or that kind of operation. So it's just like picking the value, which is like the most prominent in that neighborhood, and just using it. And because it's like coming from the actual image we had, so the quality is pretty good. Okay, so now one drawback of median filter is if you think about this, mean filtering, Gaussian filtering, whatever you do, it's a linear combination. So the computation cost is not that high. But in case of median filtering, to get that pixel value, you will have to first perform sorting, right? So you'll have to take all the values in that neighborhood and perform some kind of sorting to get the median. And that sorting operation is actually computationally expensive. And that's why we don't do median filtering. Now, another important point, I think, when you solve your programming assignment on filtering, this will come up. What should be the size of your kernel? All right. And there's a very simple rule of thumb for Gaussian kernels. Whatever standard deviation you have, you just set like half width of your kernel to 3 standard deviations. Okay. So the intuition behind that is, for example, you have this green Gaussian kernel. All right. So this is kind of a thicker. Thicker means it has a bigger standard deviation because the values are deviating a lot. And if it's like a very high peak, for example, like this blue over here, it means that it has a small standard deviation. All right. So what happens is you don't, of course, want like a very big kernel which has all the values 0. Okay. So what we try to do is we try to clip at this location where the Gaussian curve is actually going close to 0. And that value actually turns out to be 3 sigma. And that's why what we do is we take 3 sigma here, 3 sigma here, and we just discretize this curve. And that will give you your Gaussian filter. And the same holds true even if you have a 2-dimensional kernel. All right. Now, another interesting question is like what happens if we have edges, because we can't place your kernels on the corners. And there are many different solutions to that, and we should actually not worry about that. So we can actually extrapolate those values. We can actually even just make them all 0. Okay, that's called clipping filter, something like this. This is your smoothing filter. You can wrap around, which means that you can rotate the values, the pixel values. You can consider that this was like a cylinder, right? And what will happen is your values will navigate from right to left and maybe top to bottom. Okay. Then it will look something like this. And you can see that it's happening because the pixel values were being propagated from this right edge to the left edge. And you can see that the pattern is actually exactly like this. And that will be the filtering operation. You can actually copy edges. That's actually also easy. You can just extrapolate the pixel value towards the right or top or left. Okay. It will be something like this. You can see like the values are actually just extending. Okay. And there are many other ways, like you can do all that.